Hey, hello, ib2 higher level students. Okay, we finished chapter related with Faraday's law, Lenz's law, generation of electricity. Our next chapter is extension of nuclear physics. So today I'm going to talk about photoelectric effect as a first topic of new chapter. Photoelectric effect. Okay. Please pay attention. I hope you are prepared to the lesson. You have notebook, you have pen, pencil, eventual calculator. If not, stop video for a moment, organize this, and let's start the lesson. Okay, so a photoelectric effect is important. Einstein got Nobel Prize for this phenomenon, not for theory of relativity, but for photoelectric effect. Okay, so let's start from the beginning. Let's imagine an apparatus. You have a kind of metal plate, okay? Second metal plate, and this is placed in vacuum. Okay, there is a small, let's say, window through which light can enter on the metal plate. So let's imagine that light enters through the window and hits metal plate to the left. Okay, what is the result of this? The result is that electrons, which are originally on this metal plate, are removed from the metal plate and travel towards the other plate. Okay, so what is the photoelectric effect? Photoelectric effect is the emission of electrons by a metal surface when this metal surface is illuminated by light. Okay, this is the shortest description of photoelectric effect. Okay, so let's imagine that this is a part of the circuit containing a variable power supply connected in this way, containing an ammeter which is able to detect very small current, and containing, of course, a voltmeter to see voltage produced by this variable power supply. Okay, so what was observed by Einstein? Einstein observed something like this. He used a light, okay, to illuminate a metal surface. Okay, and he thought that sometimes, I give you conditions later, that sometimes electrons are emitted, are removed from the metal. Okay, conditions will be later. Yeah. Okay, so when electrons are removed from the metal surface, then right plate is negatively charged because electrons travel from left to right plate. So left plate is positively charged. Okay, so there is a current in the circuit. To stop this current, we have to turn on variable power supply. Okay, and for specific voltage called stopping voltage, current doesn't flow in the circuit, which is registered by ammeter, which shows 0 amperes. So again, practically in the circuit we have two currents. Current created by photoelectric effect, which tries to flow in this way, in this apparatus counterclockwise, and current created by variable power supply, which tries to flow clockwise. If these two currents, current created by photo effect and current created by variable power supply, are equal, then ammeter shows 0 and no current is in the circuit. So to measure photocurrent, current created by photoelectric effect, we can measure the voltage needed to stop this current, because this current is the same as current created by this power supply. Okay? And so what Einstein observed? Einstein observed two things. First, that electrons are removed only if light, which is used to illuminate, only if this light has a frequency higher than one specific frequency depending on the metal surface. So we can write that electrons are removed only if light has frequency bigger than something what Einstein called threshold frequency, FT. Okay? If frequency of light is too small, then electrons are not emitted and we cannot observe photocurrent. If frequency of light is bigger than specific frequency which is related with type of metal, then electrons are removed and we can see a current in the circuit. Okay, so this is very, very, very important statement. This is observational fact. And second observation, what Einstein made, was the relation between intensity of light, okay, and amount of electrons which are removed. Okay, so Einstein thought that if bigger intensity of light, if intensity of light is bigger, okay, then he registered more electrons removed, so bigger current in the circuit. So more electrons removed. So current in the circuit bigger. Okay, with the same voltage needed to stop it. Okay, so these two observational facts are very, very important for explanation, because these observations cannot be explained by using wave nature of light. Okay, in wave nature of light, I hope that you know that intensity of light is proportional to the amplitude of light, is related with amplitude of light, which is related with energy of light. So if bigger the intensity of light, then bigger energy, so bigger voltage needed to stop it. Einstein didn't observe this effect. Einstein observed something else. If bigger the intensity, then voltage needed to stop electrons is the same, but current in the circuit is bigger. Okay, so it's very, very, very important that this effect, these facts, cannot be explained by using typical wave nature of light. Okay, so what Einstein proposed? So his explanation is completely different. Okay, Einstein stated that light consists a lot of let's name it particles of light called photons. Okay, so we can write that light consists of photons, each of energy E equals Planck's constant times frequency of light. What is important in this? In this statement, we have two very important informations. First of all, light consists of photons, which means a parts or portion of energy. Okay, so you can imagine that each light particle called photon carries energy which is equal Planck constant multiplied by frequency of light. So if you have stream of light, then this stream of light consists of photons, and each of these photons in the stream of light has a packet of energy which is equal Planck's constant multiplied by frequency of light. Okay, second, frequency is responsible for energy of the photon. If bigger the frequency of light is, then more energy is stored in the photon, is carried by the photon. Okay, so if you have, let's say, 5 photons, each of these 5 photons is independent and has energy which is equal Planck's constant times frequency. Remember that Planck's constant is small in standard units, 6.63 times 10 to the power of minus 34 joule times second. So due to the Einstein's explanation, the light is a stream of photons, and each photon has a specific energy which is related with frequency of light. So if you have monochromatic light, you have stream of photons, each of the same energy. It's very important because in this case energy is quantized. Okay, each photon has a small amount of energy, and stream of large number of photons is the total energy of light. Is it clear? Please copy this and Next. Electron to be removed from the metal surface needs a certain amount of energy called work function. Is it clear? So let's write this. Electron to be removed from the metal surface needs or requires a certain amount of energy called work function. Okay, and this work function depends on the type of metal. Different metals have different work function. In different metals, electron to be removed needs different amount of energy. Okay? Yeah. So let's look. So now let's imagine something like this. That photon, which carries energy, let's say that collides or hits an electron. If this energy is high enough, okay, if energy of the photon is bigger than work function, then electron is removed from the surface. Okay? If this energy is not enough, then basically electron is not removed. So all depends on the fact that electron is removed or not depends on the energy of photon, which depends on the frequency of light. So this is why photons can remove electrons only if they have a frequency which is bigger than one specific called threshold frequency. And what is important here, that one photon can remove only one electron. There is not something like accumulation of energy, okay? Electron cannot wait for, I don't know, 5, 10, 15 of photons and cannot absorb of energy of 15 of photons to be removed. This is something like one-to-one interaction. So write this, okay? That one photon can hit only one electron. Okay? And if energy of photon is bigger than work function, then electron is removed. Okay? If not, of course, if it's smaller, then electron is not removed. So if not, then not. Then electron is not removed. Electron is not removed. Important here is one-to-one interaction. One photon, one electron. There is no addition of energy. Okay? And if energy of photon is bigger, then electron is removed. If it's smaller, then an electron is not removed. How can we write this? By using an equation. Okay, equation is simple. This is something like law of conservation of energy. Let's look. Energy of photon is shared between work function, so energy needed to remove electron from the metal surface, and the rest of this energy is delivered to the electron in the form of kinetic energy. Okay? So if photon has high enough energy, then electron is removed, and the rest is kinetic energy of this removed electron. So let's look. If bigger the frequency is, then more kinetic energy electron has, which means that bigger voltage is needed to stop it, which confirms observations. Okay, we can write this in a little bit better form. HF is equal to work function plus kinetic energy. And this equation, or law of conservation of energy in this phenomenon, okay, is description of photoelectric effect. And remember, this kinetic energy is kinetic energy of electron. So if you want to calculate electron speed, you can use simple equation for kinetic energy and speed. If you want to calculate voltage needed to stop electrons, you can use formula linking kinetic energy with voltage. Q times V, where Q is charge of electron, which is constant. Okay, so what is important here? Important is that frequency of light means energy of single photon. Bigger the frequency is, bigger energy of single photon. If photon's energy is high enough, bigger to the work function, then electron is removed. If not, electron is not removed and photoelectric effect doesn't take place. Okay? Second very important is stream of photons. Stream of photons is related with intensity of light. So if intensity of light is bigger, then we have more photons. Each of the same energy equals h times f, but number of photons is bigger. More photons can remove more electrons, but each electron of the same kinetic energy, which is equal q times v. Okay? But more electrons means bigger current in the circuit. Okay, let's write this. I hope you've copied. If not, please stop video, copy this. When you will be ready, start again. So let's look. We have two parameters of light. Frequency of light. Okay, frequency of light means energy. Okay, so if frequency is too small, then what happens? Then energy is too small. If energy is less than work function, okay, then no photoelectric effect. Electrons are not removed. Okay, moreover, bigger frequency, let's assume that energy is bigger than work function, so a photoelectric effect takes place. Then bigger frequency means more kinetic energy of photons, electrons, of removed electrons. Okay, what does it mean? Bigger kinetic energy means bigger voltage is needed to stop current in the circuit. This voltage needed to stop current in the circuit is known as a stopping voltage. Bigger voltage is needed to stop current. So bigger stopping voltage. Okay, so this is about frequency, yes? So frequency must be high enough to emit electrons, to remove electrons, and if frequency is high enough and increases, then more volts is needed to stop electrons because electrons have more kinetic energy. Okay? So it was about frequency of light. Second parameter which can be changed, which is related with light, is intensity of light. Okay, what does it mean? Intensity of light means number of photons. So if intensity of light increases, okay, then the number of photons also increases. We have more photons. More intense light means more photons. But each photon has the same energy because intensity doesn't influence energy of single photon. Only frequency influences energy of single photon. So let's write this. But energy of single photon is the same. Okay? Energy of single photon is the same. This is important. Yeah? Okay, we have more photons. What does it mean? If more photons, then more electrons emitted. But each of these electrons has exactly the same electrons removed. Each of these electrons has exactly the same kinetic energy. So stopping voltage is the same. Is it clear? We have more electrons, but each has the same energy. V stopping is the same. Okay, you can imagine. Let's imagine that you have a light of one intensity, which is represented by two photons, each of energy h times f. Okay, by using blue, I'm going to sketch a light which is 2 times more intense. 2 times more intense means that we have 2 times more photons. So in this case, we have 4. Okay, but each of these four has hf of energy. So total energy of light is of course bigger, 2 times bigger, because we have 2 times more photons. But energy of single photon is the same because energy is related with frequency. Is it clear? So to sum up, we have 2 parameters of light which are related with photoelectric effect. It's frequency of light, which influences energy of single photon, which says that a photoelectric effect takes place or not. If it takes place, then increasing the frequency means increasing the kinetic energy of removed electrons. And second parameter, intensity of light. Intensity of light means number of photons. If bigger the intensity, then more photons, and when photoelectric effect takes place, then more electrons can be removed. Okay? And one more parameter, work function. Work function is related with material. Each metal has own work function, which says how much energy is needed to remove light. Has exactly the same amount of energy. Kinetic energy of removed electrons and frequency of light. So vertical axis is kinetic energy of removed electrons. Horizontal axis is frequency of light. Okay, frequency, kinetic energy. This is sketch graph, so no units. So let's look. What is the shape of the graph? A minimum energy, there is a certain amount of energy which is related with specific frequency called threshold frequency, which is needed to remove electrons. If light has threshold frequency or bigger, then electrons are removed, and of course if bigger the frequency, then bigger kinetic energy of removed electrons. Okay, so this is the shape of the graph. But if you will elongate the line, yes, then line crosses y-axis, axis with kinetic energy, at specific point. What is this point? This point is negative work function, because Einstein's equation describing photoelectric effect is Hf, energy of photon, is equal phi, work function, plus Ke, kinetic energy of removed electrons. Okay? Let's rearrange this formula to obtain this relation what we have on the graph. Kinetic energy is our dependent variable, is equal to h times f minus phi, which is a straight line function, y equals mx plus b. So let's look. Our negative phi, negative work function, is y-intercept. So this is why we have phi here. Is it clear? Our Planck's constant is a gradient. Okay, so gradient is Planck's constant. We can write gradient equals Planck's constant. Of course, kinetic energy is on y-axis and frequency is on x-axis. So again, gradient of the graph is a Planck's constant, and y-intercept is negative work function. So if you have a graph how kinetic energy of removed electrons depends on the frequency of light, then gradient of this graph is a Planck's constant, and y-intercept of this graph is negative work function. So you can use graph to find these two quantities, Planck's constant and work function. Okay, I hope that you like this video lesson. Read this lesson 2-3 times more. It's not difficult. You have one equation. Next lesson will be about details related with photoelectric effect, and we will solve some examples. Okay? Thank you for watching, and see you next time. Learn physics. Bye!